Okay, so in this particular problem, we're going to be covering a number of different topics. First thing that we're going to be covering is the concept of ionization energy. We're going to be touching upon electron configurations of the two elements that we have listed in our table. The idea of nuclear charge, okay. Obviously we have two different elements, we have two different numbers of protons associated with, so that's got to be involved with the nucleus. Atomic size, and also the concept of valence electrons and where they exactly are and what proximity and so on and so forth. So this particular question that we're talking about, this is more of a theory question than anything else. There's no real calculations involved over here. So whenever you answer these types of problems, you got to make sure that you are short, sweet, to the point, and succinct, okay? There is no advantage to trying to go through a long-winded, detailed explanation when only a few words will suffice. Okay, so we've got our question here in the following table. I1 and I2 are the first and second ionization energies respectively. We've got two elements listed here where we have element is sodium. The first ionization energy is 496. The second ionization energy is 4563. It's almost a 10-fold jump over there. Notice how big a jump there is. For magnesium, you don't nearly have as much of a jump. First ionization energy is 737, and the second ionization energy is 1450. It's bigger, but not nearly as much as we had with sodium. So they're asking us, in terms of atomic structure, explain why. First question is A. I1, the first ionization energy for magnesium, is greater than the first ionization energy for sodium. Well, let's take a look at the electron configuration for sodium. We have 1s2, 2s2, 2p6, 3s1. For magnesium, 1s2, 2s2, 2p6, 3s2. Now, when we're talking about valence electrons, those are the ones that have the electrons that have the highest principal quantum number. They're the outermost electrons. Okay, so magnesium has two outermost electrons in energy level n equals 3. Sodium has one valence electron in energy level n equals 3. So they're saying the first ionization energy for magnesium is greater than it is for sodium. You notice that it's 737 versus 496. They're saying, why is that? Well, first of all, magnesium is element number 12 of the periodic table. So therefore, it has more protons. "12" to be exact, than sodium, which has 11. So in both sodium and magnesium, the electron is removed from the same 3s orbital. So since magnesium has more protons, additional protons means a higher effective nuclear charge. So you have a higher effective nuclear charge, but what does that mean? That means that the valence electron is harder to remove from magnesium than sodium, okay? You got 12 positive charges that are holding on to those electrons, okay? The 3s electrons are relatively the same distance apart from the nucleus itself. If you have a higher nuclear charge, that means that they're going to hold on to those outside electrons a little bit more dearly, okay? If you have a decreased number of protons like you have in sodium, you have one less, then you don't have as much of an attraction over here, so it's easier for that electron to come off if you apply enough energy. So that's the reason behind this. It's effective nuclear charge, higher effective nuclear charge. Notice that we are short, sweet, to the point. No need to go into a long-winded explanation with all kinds of paragraphs or anything like that. 1-2 sentences, that's all that's needed over here. Part B. They're saying that the second ionization energy for sodium is greater than the second ionization energy for magnesium, 4563 versus 1450. Okay, so then in that case, then notice the electron configurations that we had listed in part A. We have 3s1 here, 3s2 over here. Okay, so if I remove the first electron from sodium, I'm removing a valence shell electron, okay? The second one that has to be removed now has to go to the n equals 2 level, which is a smaller principal quantum number, which means that it is effectively closer to the nucleus. It is feeling the effect of the nucleus as far as the positive charge is concerned. It's awfully difficult to remove an inner core electron than it is to remove a valence shell electron. So the second electron removed in sodium comes from an inner shell or core, 2p orbital. It's close to the nucleus, it's harder to remove. Now, the second electron removed from magnesium is a valence electron in the 3 orbital. Specifically the 3s orbital. So remember what we were talking about. Here we're talking about valence, here we were talking about core. So electrons in the core are closer to the nucleus. And then in that case, then they are harder to remove. and they're held more tightly. Then the valence electrons. So remember, short, sweet, to the point. Your main things: core electrons, valence electrons, higher effective nuclear charge. Those are your three main words over here, or sets of words, that are needed in order to answer the problem effectively. So that's the reason behind the behavior that you see in the table.